Hello everyone. So we will today discuss the final part of neural networks for computational intelligence course. And last time we talked about fully connected networks. We discussed how to implement such networks in PyTorch. And today we will continue with architectures or components that are suitable for processing images, namely convolutional neural networks, and later we will discuss how to process sequences using recurrent neural networks. And the final part will be about processing, for instance, images in an unsupervised manner using autoencoders. So let's start with convolutional neural networks. If we look at fully connected nets, so we have a Bayesian component. This is a linear layer, and it combines every single neuron processes all inputs. All right. So here we have a very simple example with two neurons. The blue neuron has own set of parameters, and it processes every single X, and the magenta neuron processes all X's with own parameters. So again, what we discussed during the first lecture on neural networks, we can say that these are some feature extractors. All right. So we can say that actually every single neuron acts as a kind of this feature extractor, but it looks at this whole input. All right, so we can say that it processes some global information. So it looks at everything and provides information about what's going on there. However, in reality, we have a lot of repeating patterns. For instance, on the left, we see that there is a signal and it has some part of cosine or sine function, and then it reappears again after some time. On the right, we have digits of the same handwritten digit, but written in a little bit different way. But of course, they are very similar. They share some similarities. And if we have a bigger image with 3 digits on it, and if we now change position of these images in this black square, then we would like to highlight where are these, or notice where are these 2's, right? These digits. While if we look at it as a fully connected network, every single neuron will specialize to very specific positions because it looks at it as a whole, as one image, instead of looking at parts of these images. So, in other words, what is the message here? The message is that we need somehow to process information locally instead of only globally. All right? So there's a difference. It's global, local processing of information. So what if we go in a different way? What if we apply shared but small fully connected network? So here we have some small fully connected network with two weights, W1, Wi1 and Wi2, and we apply them to only parts of input. So here we apply this to x1 and x2, and then we jump and we apply exactly the same small fully connected network, but only locally, right, as a shifting window, and we apply them then to x3 and x4, and we look what is the output of it, what is the, let's say, the so-called feature map, right, at these positions. And of course, now we have this shared small fully connected network applied locally, and now we lost this property that we have multiple neurons, right? we cannot say that these are multiple neurons. This is, let's say, some one neuron applied multiple times locally. But of course, we can apply multiple of such neurons locally. So we can apply some other neuron, this is denoted by B, and another neuron, this is denoted by C. Okay? So now, think of it as small neural networks, fully connected neural networks, that are applied locally, like, shifting window, this manner, and they in some sense they look for some small patterns in input. Okay, and in other words, we can call it, and it is called a kernel. Okay, this small shared fully connected network, it's called a kernel. And this is the idea of convolutional neural networks. Okay, so use this small networks locally. And of course, what if we have, let's say, improper number of inputs, so that we process 2, then we jump to the next 2, but now we cannot jump to the next 2 because we have only 1 left, right? So what we can do, what we can do with this last element, we can just add artificial 0 and simply apply this shared small fully connected network to this artificially added 0. This operation is called padding, and it's widely used in convolutional neural networks to keep dimensionality proper. However, what if we don't want to move jumping to the next 2 inputs? So in other words, we allow overlapping, so we just move by 1, right? This is of course possible. We can just move by 1. So now we see that we process first 2 elements, then we process second and third, then we process third and fourth, and then we process fourth and fifth. What is the difference? Take a look. If we jump, right, by 1, let's say with padding, if we jump, so we always process 2 at once that are non-overlapping, we end up with 3 outputs, while when we move with overlapping, we have 4. And moreover, the first and last element, they are processed only once. Okay? So in order to apply convolutional neural networks, we need to be also aware how many outputs, what is the size of the output. Okay? So when you design your convolutional neural network, you need to upfront you need to calculate these numbers probably to design it in an appropriate way. So to sum up, so here we have another example that actually we have only 3 inputs, but by applying padding and this overlapping, we can get even larger size of the input. Okay, so be aware of that. What you are doing, what you want to achieve, okay? And some now nomenclature. So the size of this local FCN, fully connected network, it's called this size of kernel. It's called the kernel size. The moving, how it moves, it's called striding. It's a stride. So if we move by 1, it means that we have stride 1, and then we have overlapping processing. This kernel moves in an overlapping manner. If we want to jump by 2, so we don't process anything twice, so then we have stride 2, and so on. If we add padding, if we add zeros, we have these artificial zeros in boundaries. So these are the most important hyperparameters of convolutional network of a single kernel. We need to specify it. And here in this example, we have kernel size 2, we have stride 1, and we have padding 1 on both sides. Here, if we don't want to make this output larger, we want to make it smaller in fact. So we can use, for instance, kernel size 3, padding 1, but stride 2. So it means that we move this kernel by 2, and the element in the middle will be processed twice. Another very important element of convolutional neural networks is something which is called pooling. And there are two options of pooling. There are other options, there are multiple options of pooling actually, but the most commonly used pooling operator is max pooling, where we take, again, we move in the same way as convolution, so we have some kind of kernel moving, but let's say the activation function is we don't do any matrix multiplication inside in pooling, but we just pick a maximum element, or we average all elements. Okay, so this is how we create output of a pooling layer. And pooling layer is important because we can be locally invariant to some changes. Okay, what does it mean? It means that if we pick max or average, if we have let's say let me go to Paintbrush. So if we have pooling 2 on 2, right? If I have 1, -1, 3, and 8, so max pooling will give me 8, average will give me, so we have 0, 12 divided by 4, 3. Now, if I change positions, what I get from max pooling, ladies and gentlemen, 8. What I get from average, 3 again. Why? Because it doesn't matter how they are organized in this small local part of this input. This means these are invariant to what? Invariant to positions, right? In this small local field. We can come back to our presentation, all right? So now we introduced a different layer, so this pooling layer. It is very useful because it can make our neural network a bit more robust to some local changes. So imagine that you have a small slight change in color or something like that. So it will be robust to this. Okay. And how convolutional neural networks, how do they work on images? So let's take a convolutional so-called conv2D layer, and we have an image consisting of 5 by 5 pixels, okay? So, and we have 100 digits, we see that this is number 4. And how it works? So we have a kernel, let's say 3 on 3, right? So in this kernel, so this is this small, fully connected neural network that will be applied element-wise. So in every single cell on the right figure, we have some values, okay? And we just simply apply it to this region, okay? As this is depicted on the left. And this produces us some value. Then we apply next, and we have again, we obtain, so element-wise, so left top corner is applied to left top corner in this part of the image, and middle is multiplied with the middle pixel of this image, okay? And so on, and we can proceed, and so on. We move in this manner, so we'll take a look. So we are moving from top left to the right, we move down, which means that striding is 1 in both directions, and so on. Okay, no padding. So we create, so with kernel size 3 and padding 0 and striding 1, so we create a new image or new so-called feature map, 3 on 3. Okay, so this is how a convolutional network layer works. So let's say that here is an example of that again to see. So we have kernel 3 on 3. Let's say here we included padding, so we have 1 and 1. So both borders are expanded with zeros, and we have striding, for instance, 1 1. Okay. So this is how. So we said that convolutional layers, they process data as locally, right? So we this is So we process it locally, and we can spot recurring patterns or similar patterns in different places. But of course, the question is it possible to classify everything, for instance, to process everything only with local information? Well, not really. Ideally, it should be like we should be able to spot recurring patterns in different places, process them. We can say, hey, here is this pattern, here is this pattern. And then we should be able to combine all this information again. So apply global processing, okay? And this is how a typical convolutional neural network is designed. So first we have some conv2d layers. We get a feature map. Then we have some kind of pooling to be, to compress it, to be even further invariant to local changes, all right? And we flatten it, all these channels, and we apply fully connected layer to obtain one single output. All right. One thing that I missed so far, but it appears here. So as you can see, we have image that consists of one channel, right? This is just a matrix. But when I said that we can apply these local fully connected networks, aka kernels, we need to apply a couple of them. So you can think of it as a number of channels in convolutional 2D layer. In this example, we have 3 kernels, so 3 channels. As a result, every single kernel will process the image individually. So as a result, as an output of this layer, we'll obtain feature maps, 3 of them, 1 feature map per kernel. In other words, we'll get a new processed image, but now with the 3 channels, okay? And then we can apply pooling operators. So here is maybe this bit, it is a bit confusing. It should be just a single pooling because we just specify kernel and we go. But yeah, it could be actually, it should be actually three channels. So that the feature map consists again of 3 channels. And then of course flattening means that we take these kernels and we make from matrix, we make a vector, and then we concatenate from all channels. Okay, so we just simply make this tensor now, 3D tensor, and we create a long vector. Since we have this long vector, we are now able to apply a fully connected network, and that can classify an image. And to see in one slide, to remember what are these properties? So convolutional layers, they process local information, while fully connected layers, they process global information. And convolutional layers are good at finding patterns, while fully connected layers are rather good at combining patterns. Okay, once we provide patterns to fully connected network, it should be able to figure out which patterns I should use to classify my image. And I would say that convolutional layers are good at processing raw data, while these fully connected layers are rather good at processing already transformed data. So what does it mean? It means that because we act globally with fully connected layers, so if there is a small change in input, it could produce a large difference in the output. While for convolutional layers, since they act very locally, so small changes, they don't necessarily influence the whole output. Okay, they only influence the local change. Both of these layers are easy to stack, and we can of course build and treat them as building blocks of a neural network. All right. So this is it, what I would like you to remember from this slide, from theoretical perspective, let's say, or from this design perspective, conceptual perspective, while you build neural networks and why we use different kind of layers in neural networks, okay? And now I would like to talk about processing sequences with recurrent neural networks, okay? So of course, sequential data occurs everywhere, and it could be a sound. So for instance, the sound of is represented as a signal, right, with of some values, and this is temporal dependency. We can have a video of moving digits here in this case, or any video is that, of course, one frame occurs after the other and there is some kind of movement maybe. But we have also language, so we can have, for instance, the cat sat on the mat, and when we change order of some words, it makes no sense and the sentence is incorrect. We have also, in general, for instance, handwriting, and this is again the sequence of letters matters, right? Or the order of letters matters, because this is how we get a word. But also maybe more more abstract application or non-obvious application of sequential data is, for instance, DNA sequence. And this is also something that when some these letters occur in DNA, there is they don't occur at random at given direct positions. There is some sequential dependency, right? How they occur, and this sequential dependency is determined by biochemistry, by physics, chemistry, and so on. So not always is about time dependency, but very often about time dependency. But this sequential character of data could be spotted in many different applications, especially real life applications. And how to deal with that? There are many different problems, okay, and there are many different challenges. How to process sequential data? So first of all, how to deal with variable input length, okay? So what when we have the cat sat on the mat, then we say again, right? So these two semantically they mean very similar thing with some subtle contextual information, right? But if we want to, for instance, classify these images or answer this or do whatever with this images but sentences, so we should be able to process it, and we should expect very similar processed information, so the embedding, so-called. right? Another question is how to deal with permutations. So we can imagine not maybe fully correct sentence maybe, but why not? So on the mat sat the cat, right? So how to deal with this? And we would expect that the cat sat on the mat and on the mat sat the cat. They are somehow semantically the same. Maybe we should expect the same output, right? So the processed version of this sentence should be very similar. And how to learn sequential dependencies in the first place, right? What if we say the mat sat on the cat? It makes no sense. So maybe when we want, for instance, generate sentences, we should avoid such kind of sequences, right? Such sentences. So we should somehow enforce our model to learn sequential data. And again, I want to sell you this idea that let's start with fully connected network that is shared, but now it has also some extra input, and it will be applied in this case to each individual word. Okay, so we start with processing every single word with the same fully connected network. But this is of course not the end, because right now we don't have any sequential processing. It's just that we can actually permute these words, and applying this fully connected network, well, they will produce exactly the same outputs. But if we now pass what was the output of previous, let's so-called state, or in this case previous word, so we should be able to now learn or influence what comes out from previous moment, right? From previous state. So if we start with the, and then we add 0 because we don't have any history, all right, we process it. Then we process cat. We take what was before and the current word, so we process it in this way, and so on, right? So now you see that we have some kind of memory what was going on in the beginning. So the sequentiality of this comes into the game. On top of that, if we want to classify sentences, of course, we can add another fully connected network that will classify the sentence. And if you look at it, so the last blue fully connected network block, it already has, indirectly, but it already has access to everything else what happened in the past, because the previous FCN block processed already what was before, and so on, so on. So here is the recurrent character of this neural network, okay? Obviously, if you want to maybe use it in an unsupervised way, you of course maybe don't need this classifier in the end. But this is a very typical, very standard structure of a recurrent neural network with a classifier on top of that. But of course now, the magenta color is on purpose because it's this fully connected network block. It doesn't share parameters with the blue one, okay? And in general, there is nothing to be, we are not forced to use fully connected networks. We can use any neural network inside. And this is a general scheme for recurrent neural networks. It could be, if we have a video, if we process video, then of course this blue block could be a convolutional neural network. If we use we can use some specialized neural networks for recurrent neural networks, and so on, okay? So yeah, as I said, there is nothing against to use other neural network, but this is the general scheme, okay? What are positive pros and cons, right? So with such architecture, the simplest recurrent neural network, we can process repeating patterns by using a shared NN block, neural network block. You know, this neural network block could be a deep neural network by itself, okay? So again, this could be any neural network, any architecture there. Another thing is that we can learn sequential dependencies by including outputs from previous blocks. We can deal with variable length of a sequence, because if we look at this, and the last output of neural network, the blue block, it actually doesn't matter how many blocks we had before, because we already somehow passed this information from previous block to the last one, okay? So this is actually really nice. We are invariant. For us, doesn't matter how many elements we process. And of course, we can use also backpropagation to learn a recurrent neural network, right? If we look at it, and if we look at it as, as stacked neural networks, everything with this blue or magenta block, they are defined with forward and backwards paths, right? So it's easy to calculate gradients in an automatic manner. So no problem here. What are cons? So learning could be tricky. For instance, vanishing gradient problem could occur. So when we will have, for instance, in one block, it becomes 0 somewhere, so then it will propagate back to the beginning, and basically we don't learn much. It turns out that when sequences are longer, so there is a problem with learning long-term dependencies. It turns out also in practice that not always this is prone to permutations. For instance, for video classification, there are papers that they play video normally and then in reverse, and it turns out that the recurrent neural network classifies this in the same way, which is a little bit weird because, for instance, we would expect that, or even they permuted frames in video. So normally, as human beings, we could be confused what's going on, but neural networks are not so confused. So there's a vast of papers on how to deal with sequential data. I would say that it's still not solved. It's still very tricky. Learning could be very tricky. There are some tricks, but I would say this is one of open problems in deep learning. Okay, how to learn sequential models. But for some simpler cases, recurrent neural nets are perfectly fine to be used. There's vast of possible extensions. Okay, so you can use convolutional neural networks in place of fully connected networks. Obviously, you can use a very specialized construction of a block, so-called long short-term memory, or gated recurrent units. There are two ideas how to deal with this, remembering what's going on in the beginning. There is idea of clipping gradients. So there is this time backpropagation that you don't update everything to the beginning. You just cut it at some point. You clip gradients not to blow or not to vanish or something like that. You can take outputs from multiple previous steps. So then, of course, you will have a little bit like this second order Markov chains or third order Markov chains, and so on, so on. So you can use many different ideas, but still, most of them they don't work in any case. They are good for some cases, better for others, worse for others. Okay. So, but it's still a very nice and interesting field of study. And the last topic for today are autoencoders. So if you attended machine learning course, you had autoencoders, you talked about variational autoencoders, but here I would like to be to maybe repetitive and for some of you or all of you, but it's good to remember that we can also build unsupervised models out of neural networks. So how it works? So in general, we can use it for different tasks. So for instance, we can use it for compression. So if we use a compression, so we use some kind of encoder, decoder, right? So from a big image, we encode it, we compress it to some smaller code in general that then could be further decoded back to the image. Of course, we can lose some information about specific shapes, but still more or less we see the same. We can use this auto-encoding scheme to reconstruction to denoising. So let's say that we have image, this is noise, you see some pixels are blacked out, some gray ones are added. So of course, and if we have a trained autoencoder and we just encode it to the latent space, so-called this code space. So then if we decode back, so we should remove this or some of this noise, because we learned the clean versions of these images, okay? And another application is in painting. So in painting, it's something like, you can say, very severe and intentional denoising of image. So for instance, we cut half of this image and we hope that our model is trained on clean images, so it's able to recover the good clean image, okay? So you see that it's recovered 2, but of course the lower part is this average maybe version or clean version of 2. So for all these tasks, right, compression, denoising, painting, I started talking about autoencoder. So it means that we have this encoder that encodes images to the latent space, and we have a decoder that decodes it back from latent space to the observable space. And a natural question is, of course, in so far in many of these applications, so there are very specific models proposed to deal with these cases, like for compression. So we have different codecs, vocoders, so for audio, for voice, and so on, so on. So people designed these codecs for denoising. So people used even physics, apply complicated formulas to somehow get rid of noises. They assumed what kind of noise I have and how I can deal with that, and so on, so on. But of course, a natural question is, could we simply replace encoders and decoders with specific neural networks so that to solve this task? So for instance, the compression task, like we ask, right? But anything else in this scenario that we have encoder and decoder? And the answer is, of course, yes. So let's say that we have an image. So this is a 4, let's say. We implement the encoder using some convolutional layers, right? And in the end, I get a code. And then I use another neural network, but somehow that mirrors the architecture of an encoder, so that I get back the good shape, right? Because in the end, I must have the same shape as my original input. And that's it, basically. So this is the idea of autoencoders. Now the question is, what kind of objective function I should use? So you can use simply, you can use, if the data is real valued, so you can use the L2 norm. So just to calculate difference per pixel or per dimension. Or if we have the binary data, we can use so-called cross-entropy loss. This binary cross-entropy, and then of course decoder outputs something that is close to probabilities, right? And so in both cases, take a look that we first encode. So we have this e of actually on the left and on the right should be e of x. Sorry, there is a mistake. And then it decodes back. So it is a composition of encoder and decoder. And this is everything for this lecture. And with this lecture, we end neural networks. I know that it is more like a brief introduction to neural networks. I hope that it is enough to build some neural networks, that you have some impression of neural networks. And I really do hope that you will learn more from the assignment, okay? And you will play with these different architectures and how they behave. After this course, so my idea is that you are familiar with optimization methods, but I also wanted to have at least one class of models that you can optimize using some optimization method. I think that neural networks nowadays, they are these leading methods, so this is useful for many applications. I also do hope that some of you will get more excited about neural networks and you will continue studying this aspect. So deep learning is of great interest in my research. So if you have, after this course, you have some ideas, you want to follow bachelor thesis with someone, so please give me a call and we can maybe think of some interesting and exciting topics. All right, thank you very much.